So when we first started taking notes about derivatives, we wrote that derivatives had some applications with slope and also rates of change. So now it's time to talk about rates of change. So it's determining the rate of change of one variable with respect to another. Rate of change of one variable with respect to another. So we could talk about, so it says it occurs in a wide variety of fields. A few examples would be population growth rates, and the two variables we'd be talking about there would be the population and the time. So it'd be how much did the population grow over the past 5 years, so growth rates. Another would be maybe like water flow rate, how much water entered the tank in the past 10 minutes. Velocity, what is the change in the distance over the change in time. Acceleration was the change in speed over time. So production rates, how much of the product did they produce over a certain amount of time. Often time is one of those variables that we're talking about. And a common use for rate of change is to describe the motion of an object moving in a straight line. And I'm putting quotes around line because they will often mean a curve and not just a straight line segment. And this is where we were talking about physics, people. So if we come up with a positive rate, or let's say a positive direction, then that could be up or to the right. And if we were moving in a negative direction, that could be down or to the left. And both of those things make sense on a graph. So now we're going to get to this thing called a position function. It gives the position relative to the origin. Of an object as a function of time. And it seems strange, but S is the variable that we use for the position function. So S of t is our position function. And if over a period of time, delta t, the object changes its position by this amount. So they said the position, delta often means change in math. Delta S is S of t plus delta t minus S of t. So if the position changes, so if over a period of time delta t oops. The object changes its position by this amount. Then they're saying we can use that distance equals rate times time formula, that DIRT formula. Instead of this way, though, they want to solve it for rate. So rate would be distance over time. And average velocity, which is a rate, is the change in distance over the change in time. Distance would be a marker of position. If we changed our distance changed, we changed our position. So this is the little formula for average velocity. And that brings us to example 9. Change in position over change in time. Change in distance over change in time. All right, so example 9, they are dropping a billiard ball in your book. You can look on page 112 with me. They're dropping a billiard ball from a height of 100 feet. The ball's height s at time t is the position function. So they're giving us a function to model this scenario. They're dropping it from 100 feet. The ball's height s at time t is given by this function, where s is measured in feet and time is measured in seconds. Find the average velocity over each of the following time intervals. So A was find the average velocity over the time interval 1 to 2. So we can use our average velocity. We can use this that I've boxed here at the bottom. Average velocity is the change in position over the change in time. The change in position, we actually need to do just a little bit of work here. Instead of maybe just saying S right here, maybe we want to say S of t. Okay, so change in position would be the position at one endpoint in that interval minus the position at the other endpoint over the time in seconds just subtracted. So here's our two values, our A and our B. It's like S of B minus S of A over B minus A. That's what I'm doing. So S of B, we're going to put 2 into the position function and work it out. Negative 16 times 2 squared plus 100. That's negative 64 plus 100, which is 36. And S of 1 is negative 16 times 1 squared plus 100. Negative 16 plus 100 is 84. So we got 36 minus 84 over 2 minus 1. That gives us negative 14 minus 6 is 8, 7 minus 3. Negative 48 over 1. So it's negative 48. So let's think about that for a second. If the average velocity is negative 48, let's get our units. Position was in feet, time was in seconds. So this is all feet, and this is seconds. Feet, seconds. So this is negative 48 feet per 1 second, or negative 48 feet per second. what does that mean? That negative describes its movement. It's either going down or it's going to the left. Well, in this scenario, they are dropping a billiard ball, so it's dropping down. So it's going 48 feet per second down, or it's falling 48 feet per second. All right. And I forgot when we were over here and talking about rate of change, our book might also say instantaneous rate of change, and that is, these are interchangeable. Instantaneous so we treat those the same. Rate of change is sometimes referred to instantaneous rates of change. Okay, so now they're extending this thinking a little bit, and they're saying, let's find the instantaneous velocity, or just the velocity when t is 1. Let's find its speed exactly at 1 second. How fast is it dropping? Well, to do that, that would just be 1 point, not an interval between 1 and 2, not where we have two different values. We would just have one value, and that equates to that curve. If you want the slope of the curve right there at that tangent line, well, how do we do that? We needed to use 2 points on a secant line and move them closer and closer. So it's a limit idea. So the instantaneous velocity, or the v of t, just the velocity, could be found doing the limit as delta x approaches 0. Delta t. Of s of t plus delta t minus s of t all over delta t. Well, we know that when we did this limit process, we said we were finding the slope of the tangent line, and then we learned that it was also the derivative. And this is the derivative of this s function, so this is actually equal to the derivative of the position. Not hugely important that you would think to write this out, but the derivative of position is the velocity. So s prime of t, the derivative of position, is velocity. They're equal to each other. So in other words, derivative of position is the velocity. And one last thing right here. Speed is the absolute value of velocity. Because speed is always positive. Even if an object is falling, its speed, like our billiard ball was falling 48 feet per second, but its speed that it was falling at was 48 feet per second. And this is super important. The position of a free-falling object like our billiard ball. They just opened up their hand and dropped the billiard ball. They didn't shoot it out of a cannon. They didn't throw it with any force. They just dropped it. Is found by s of t equals 1/2 gt squared plus v naught t plus s of naught. G is the acceleration due to gravity. And if we're doing these experiments on Earth, then G is negative 32 feet per second. And you need to ask Miss Peterson about that feet per second stuff. Or it's negative 32 feet per second squared. Or if we're in meters, it's negative 9.8 meters per second, which is negative 9.8 meters per second squared. And I think in physics you all round these, but we use negative 32 and we use negative 9.8 in calculus. All right. Okay, so the last thing I just thought I would show you was they were talking, they said if we wanted to see where this negative 32 feet per second squared came from, then we could do the limit of the position function, and we could use 1 second for t and 0.1 for delta t. So that's just a little change off of 1 second, just adding 0.1 to it. And so if we use that amount of change, then we ran through the position function right here with those values, 1 plus 0.1 minus s of 1 over the time subtracted, the 1 minus the change. And then we ran through 1 plus 0.1 would be 1.1. And then if we plugged 1.1 into this position function, and then we plugged 1 into this position function, that's what it would look like here. And then we would get this minus this over 0.9, and we would get 39.3. And I'm trying to get 32 feet per second squared. But we used a change that was equal to 0.1. If we'd used an even smaller value, like 0.01, then our 39 would have been closer. If we'd used like 0.00001, where it was just barely a change from the 1 second we're talking about, then our limit would approach 32. So maybe you thought that was interesting. Maybe you didn't. You do not have to recreate this. We will just all memorize that on Earth, the acceleration due to gravity is negative 32 feet per second squared, or negative 9.8 meters per second squared. This V naught is the initial velocity, and this S sub naught is the initial position. And when we come to class, we will do example 10 together.